All right, solving sine 2x is equal to 1 over 2 on the interval 0 to 2 pi. So this is the double angle application where we have to find solution to that trigonometric equation where period has changed now. In the previous videos we were working with simple equations where the period was 2 pi radians. When you have an angle of 2x, so the period of the function is defined as, to grab a different pen, so the period is defined now as 2 pi divided by 2 because of that angle 2x. So this is equal to pi radians. So the full cycle of the sine function is completed on pi radians. So pi, and the next one here, 2 pi. Okay, so I'm going to show first cycle completed. The first red dot is, and then there is another one here. And let's mark it 0, the initial value. Okay, so our goal is to find when this is equal to 1 over 2. So again, imagine there's a horizontal line that cuts through the graph, and we can see from the graph that there are 1, 2, 3, and 4 roots. Okay, so I have 4 roots on that interval, and I need to find at least 2, and I know that the next 2 are just repeated because of the periodical feature of the function. So the first one, how do I get to the first one? So let's do the following. Let's say that angle 2x, let 2x is equal to, say, z. So now our equation will be defined as sine z is equal to 1 over 2. And since we may remember, if we don't remember, there's always a way of recalling special angle triangle where you can quickly identify sine ratio. Let's say if this is 1, this side will be root 3, and this hypotenuse is 2. So the ratio opposite over hypotenuse 1 over 2 will give me 30-degree angle, or pi over 6. So first you're going to say that z is equal to pi over 6. However, our goal is to find the solution for x. So knowing that 2x was defined as 1z, so 2x will be equal to pi over 6. Hence, x is equal to pi over 12. Okay, so I've got the first root. So this is the root number 1 right here. The second root, you may remember we talked about congruency of this wave above x-axis, below x-axis. Those are the parts of the graph that are identical. If I know that this is pi over 12, I can locate the 0 value, which is halfway between 0 and pi, and move to the left from pi over 2 by pi over 12 value. Okay, so, or I may remember from the past that the second solution for z, when sine is also positive, is pi minus pi over 6, which will give me 5 over 6 pi. So I can either do this way, and then let me change the color. So now my 2x is equal to 5 over 6 pi. So 1x is equal to 5 over 12 pi. Excellent. 2 roots. Well, we have 2 more to go. So, what is the period of the function? Pi radians. So, when you add to root number 1, the period of the function, so you're going to move from this point above all the way to this point right here. So that will be root number 3, and you can call it x is equal pi over 12 plus 1 pi. And this will get us, so this 12 over 12, 13 over 12 pi. Okay, so I have root number 3. How do you get root number 4? Same way. So remember that root number 2 was right here, and you're going to move it to the right. Okay, so you add pi. So the one below, 5 over 12 pi plus 1 pi will get you 17, because we have 12 over 12 plus 5, so 17 over 12 pi. Now, you may wonder, should I stop right here? Have I listed all possible roots, or is there more to that? In case you're wondering, you may wish to add pi to root number 3, number 4. If your total will be greater than 2 pi radians, you know you have gone beyond that interval. So at this point, you will stop it. So this equation, just to recap, has 4 roots. First 2 we have found using the pi over 6 value of z. The second one we did by finding the value of 5 over 6 pi for z, and then when you divide it by 2, you get the following root. By adding the period to the first 2 roots, we have able to identify the 2 more roots. So in total, we have 4 roots, and that completes our video. Thank you very much for your attention, and I see you next time. Bye-bye.